We have 45 minutes of recording left. I have 55 minutes. Wrong pin. Can you see my... No, okay, that's off camera. Good. So we're starting again. So let's say, in this case, this is, somebody said 2. 2, yes, it's 2, because it's an, right? If it's bana and kana. And what if it's 4, 4? So it's bana and kana. Yes, 3. And what if it's 3, 5? Wait. This is 5. So it's I, this is I, and J, right? So 4, 3. No, 4, 3 is 4 and 3. 4, 4 is 4 and 4. And then there's 5, 3. 5, 3. Banan and kan. It's still 2, right? Because banan, you can only get, so there's five characters here. Banan and kan, well, it's only A and N, so it's still 2. So this, it can be either, so banan and kana is either so we either have bana and kana, or we have banan and or we have 4 and 4 is bana and kana. So here we have A and A, A and A. Here we have, say, AN and AN, and here we have, wait, I've got bana and kana twice. We've got 5, 3, 4, 4, and 4, 3. 4, this sheet is here. Okay. So, which is best? Well, to take this and put an N and not match it with anything. So the longest common subsequence of banan and kana is ana. Still. Right? It's like you're trying to get from here down to here, and every time you cross a red bridge, it's because you've managed to get to a position where you have a character here that matches with a character here, and you get a point. You add the same character to both of them, and you increase the length of the longest common subsequence. Okay, so this is max of this, this, and this, so this is 3. And that's because the longest common subsequence of this and this is ana, and that you get, I'm not going to put a red arrow there, that you get because it's the same as the longest common subsequence of bana and kana. 4 and 4. Okay? So let's look at the case, let's look at the other case, because I really want you to understand this stuff. Let's look at the case where it's banana and Canada. This is this case where the two final characters do match. So this is I equals 6, J equals 6. Okay? So, what is this matrix? What are these entries? Well, this is the longest common subsequence of I is equal to 5, I is equal to 6, J is equal to 5, J is equal to 6. This is 5 and 6, so this is the longest common subsequence. Here we put the longest common subsequence of banana and canard. And that's 3, because it's still A and A. And here we put the longest common subsequence of banan and canard, and that's still 3. And here we put the longest common subsequence of I is 6 and J is 5, banana and canard. Yeah. Okay, I may have said banan and canard when I meant banana and canard. Okay, so this is still 3. But then here, we take this, we take the max of this plus 1 and this, and we get 4. And why is that the case? It's because the longest common subsequence of banana and Canada is the longest common subsequence of banana and canard with an A appended to it. Okay? Good, excellent. 2 people will pass my course. As I've said in the previous lecture, you should, well, I didn't say you should code this, but in general, if you really want to be sure you understand something, you should code it. So, like, right up, it's 2 for loops. Just have it do this. So that's longest common subsequence, which I will occasionally say longest common substring, which is wrong, because a substring has to be continuous, a subsequence doesn't. I'll also sometimes probably say longest increasing subsequence, because that's what we're going to study next week. Okay, longest common subsequence, I think that might be on LeetCode. If you can find it on LeetCode, solve it on LeetCode. It's related to another famous problem, which is called edit distance. So, it's sort of a flip side of edit distance. So, edit distance is, there are lots of different kinds of edit distance. But what's usually said is, you're given 2 strings, like banana and Canada and banana, and you're asked, how many edits does it take to change one of the strings into the other one? Where in edit, you can insert a character, you can delete a character, or you can change a character. Okay? It's very close. You also do it with the same kind of dynamic programming, but, so this is called the recurrence. Because people love using recurrence for several different things in the same course. It's slightly different recurrence. I'm still going to use the same matrix, and I'm still going to have the same red bridges. You can be thinking of questions while I erase everything. The philosophy, so what changes is, now, longest common subsequence, I'm gaining a point every time I cross a red bridge. Okay, so I'm going to change this problem definition slightly. The idea with the longest, so with longest common subsequence, you're looking for stuff which is the same, and for the stuff which is the same, you gain some sort of profit. Okay? You try to maximize the number of red bridges you cross. Edit distance, you are trying to minimize the number of edits that you have to do. So the idea, I mean, you can see how this is related, because what you could do is, given banana in Canada, if you know that the longest common subsequence is ANAA, well, what you could do is take banana and get rid of and delete all the characters. Now, this is if you couldn't do substitutions. What you could do is delete the characters to get the longest common substring, and then insert the characters, so delete the characters from banana that aren't in the longest common substring, and then insert the characters that in Canada that aren't in the longest common substring. So you turn banana into the longest common substring, and then you turn the longest common substring into Canada. But you can do substitutions, so it's not quite that easy. That would be if edit distance were the version without substitutions. But you can see that, you know, there's this idea that if there's a long common substring, then it means that if there's a long common subsequence, then you should be able to get from one to the other. The edit distance should be small. My bagel is like right there. So I was watching a PhD thesis and I wasn't eating. So although it was on Zoom and I was muted, so I could have been eating. So the idea is, now I'm trying to get from here to here, but at each step you can move right one cell, down one cell, or diagonally right and down one cell. But you don't pay whenever you follow a red arrow. So how little can you pay? I have to put in here otherwise you pay $1. Okay? So now now you're trying to, here you start off, you have paid nothing. And here you're trying to figure out how do you get here paying the least you can. And, well, it's pretty obvious that you have to pay 1 to go here, and then nothing, 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 and then 1 to go here, and then nothing. So you can pay 2, right? Which is changing this B into a C and changing this N into a D. So you can, with 2 edits, you can get from banana to Canada. But let's actually figure out how we should do this in general for big, big problems. And people do this. This is used for genetic alignment. So, for example, if they're sequencing a new species and they want to figure out how its genome aligns, that is like you trust me, this comes up in computational genomics. So let's actually see. If you knew how much it cost you to get, what's the minimum price you could pay to get here, or you could ask your friendly professor, Prof, how much does it cost me to get here? How much does it cost me to get here? How much does it cost me to get here? Well, now, what are these recurrences? Now, what is this number? So the two cases that so now what is this? Yes. This one is min x plus, well, okay. X, y, z plus 1. And this is min x, y plus 1, z plus 1. Okay? So this is pretty easy. 1, 2, 3, 4, 5, 6. I don't need any recurrences to figure that out, because how many edits do I need to change the empty string into C1, CA2, CAN3? Okay. 1, 2, 3, 4, 5, 6. And then to change B into C, well, this is min of this plus 1, this plus 1, this plus 1, so this is 1, this is 2, right? Because you could change a B into a C, so that's actually either I change, I insert a C, and then I change the B into an A, or I change the B into a C and I insert an A. So this is min of this is 3, this is 4, this is 5, this is 6, this is min, this is 2, this is still 1, right? Because how do I change BA into CA? Well, I just change the B into a C and then I leave it alone. Okay. So I'm still working, cell, if this matrix is A, a two-dimensional matrix, Aij should be the edit distance between x1 to xi and y1 to yj, right? So this is still, the edit distance between BA and CA is still 2, is 1, BA and CA. Okay, BA and CAN, the min of these 3 plus 1 is 2. Now the min of these 3 plus 1 is 3, and that can be done one of two ways. Either I take B, and so I would go here, so I would change the B into a C, and then leave the AN and then insert AN, and then this A is an A, right? So it's like I change, what is this? This is BA and CA, it's BA into CANA. I'm gonna run out of time. Half an hour, maybe. So what I can do is, first I change it into CA. And then I insert, excuse me, to get to here. So I have the option of either changing B into CAN, right, which is or so it's either I leave it like this and insert AN, or I can take BA and change it to CA and then add NA on the end, right? So I can either insert AN between the C and the A, or I can leave this A alone. Well, I can insert an N and an A afterwards. So it's the same, right? It gets me the same place, but it's two different routes. So the thing I want you to notice is that you can calculate the paths through, you can find the paths through here, and those correspond to strategies, to sequences of edits that you would do to change this string into this string. Okay, so because the search problem, if you get this number down here, that just tells you the minimum number of edits. It doesn't tell you the list of the minimum. It doesn't tell you a list of the edits to do, right? So in computational genomics, you don't want to know that the distance between this gene in the gene in the mouse and the gene in the human, that the edit distance is this. You actually want an alignment. You want, it's called a cigar string. You may have seen them. Otherwise, look up cigar string and look for one that looks like it's got DNA. If this were a normal class, I would make other people be doing this. But okay, so this is a 4, and this is a 5. And it's a 5 because, and you have two different ways of getting it, either from here or from here. Okay, I'm not going to spend any more time filling in this matrix because it's I'm sure you can do this. I hope you can do this. So that's edit distance. Do you have any questions? Is anybody listening? Of my massive 19 students. Good, okay. So there is, it's not known how to do this. So how long does this take? So each of these steps is pretty easy. But if I give you a string of length n and a string of length m, it's going to take, how big is the matrix? So these are constant time, but the matrix is m by n. Right? So in general, it's going to take me order mn time and order mn space. It's going to, if I fill in this matrix, it's going to use quadratic time and quadratic space. Now, I just said that we use this in computational genomics. You align like the mouse genome to the human genome. Well, actually, you align chromosomes. Well, you align genomes. Yeah, ignore it. I mean, you could align whole genomes in microbes. Yeah, whatever. genomes are pretty big, right? So it's like a human genome is 3 gigabytes. It's 3 billion characters. So if you're looking at 3 billion times 3 billion, that's a lot. So your computer doesn't have that much memory. So first, let's see a quick... What? Already? That was 25 minutes?